we discuss now the quadrature amplitude modulation. So the previous maybe couple of lectures or maybe 3 lectures or so, we have been discussing QPSK and the octal PSK, the 8 PSK so called. So now we move on to a discussion on quadrature amplitude modulation. Or QAM in short, or QAM in short. Now this is essentially this is a combination of amplitude modulation as well as phase modulation, and as it will be clear when we proceed with the discussion. So a typical Mraquam signal, a typical Mraquam signal, a typical Mraquam signal will be like this, can be expressed like this: square root of E naught. So E naught here is an energy term. It's not exactly the symbol energy. It is an energy term, and its connection with the energy of the symbol will be discussed later. DIM, and this DIM stands for one of the symbols. Again, things will become clearer as I proceed further. Square root of 2 by Ts cos 2 pi fct. So this term must be familiar. This is one of the basis functions, the in-phase carrier component, and that is why we have an I here to say that it is the symbol, or it is something that is associated with the in-phase carrier component, so that I is to signify that. And continuing further, minus root E naught dQm root 2 by Ts sine 2 pi fct. So dq, again this is familiar to you. This is the quadrature carrier component, that is the phi 2 t which we had earlier. It's the same thing, of course. We now call it as the quadrature carrier component. Maybe we can call it interchangeably as phi 1, phi 2, or the in-phase and quadrature carrier components. We are familiar with both the terms now, and this is the term which is associated with the quadrature carrier component, and hence that q. And these are actually the, as I said, in-phase and quadrature symbols of the quadrature amplitude modulation modulated signal. And of course t, small t, this is for small t 0 to Ts, and that tells what is this Ts, and of course this is there to normalize the energy of this, and this is also there for the same, and it plays the same function. And of course m 0, 1, 2 up to m minus 1. So this is what an Mraquam signal looks like. We can express an Mraquam signal like this, and DIM and DQM will take on values from, they will take on values independently from, or take on values which range from, they take on values which will range from, or from a basket, so to say, minus root m plus 1 minus root m plus 3 minus root m plus 5, so on and so forth, ending at root m minus 1. So of course this range is dictated by the value of m in the Mraquam. So as an example, let's say that we have m as equal to 16. That gives us a 16 quam. Mraquam, m16 means you get a 16 quam. That means there will be 16 symbols, of course. In all, 16 symbols. 2 raised to 4, 16. 4 bits will constitute one symbol. Now, if that is the case, m being 16, root m becomes 4. And this range will be minus 4 plus 1, that is minus 3, minus 4 plus 3, that will be minus 1. And then this becomes irrelevant because this is just to give the general range. Now this becomes irrelevant, and hence we, of course, it becomes irrelevant in the sense you will get 5 minus 4, that is 1, not irrelevant. I am sorry. What I meant to say is the next one, minus root m plus 7, minus root m plus 7 will give us minus 4 plus 7, that is 3, and that will be the same as 4 minus 1, that is 3. So it ends here. That's what I was trying to mean when I say this becomes irrelevant. Of course, that's a slight slip of tongue there. So this is how we decide the range of values. I will give you one more example later so that it becomes clear what we exactly mean by this range of values. So dim and dqm are going to take on these values independently. And since there are 4 different values here and there are 2 symbols here, the in phase and the quadrature symbols, which can take these values independently, you will have 16 combinations, and hence we get m is equal to 16, the 16 quam. Now a possible mapping of values of m onto the values taken by dim and dqm can be shown in the form of a table with 16 rows, and I will try to show that table here. So we need to have 16 rows, and as I said, when m is equal to 16, these are the values, range of values, these are the values which dim and dqm is going to take, and it takes these values independently. So let me show the mapping now. So we have m here, dim, dqm. So m can take on values ranging from, or can take integer values 0, 1, 2, etc. up to m minus 1. M is 16, so 0, 1, 2 up to 15 it can take. So let me write that first. 0, or maybe just to make it look a bit aesthetic, just to pay some attention to the aesthetics. I have to have 16, at least 16 rows here. So just will try to make it. I think I have ended up with more than 16, but that's fine. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Exactly 16. I have exactly 16, not more than 16. And and I will now show a possible way in which dim and dqm can take values. So for m0, I will have di0, dq0, and that can be, remember, it's going to take values from this independently. So that can be minus 3, minus 3. And then for m1, that can be minus 3, minus 1. For M2 it can be minus 3, 1. For M3 minus 3, 3. So in continuing this way, for M4 you can have minus 1, minus 3, minus 1, minus 1, minus 1, 1, minus 1, 3. And rest of it you can fill. 1, 1, 1, 1, 3, 3, 3, 3. And of course you have minus 3, minus 1, 1, 3, minus 3, minus 1, 1, 3. So starting from minus 3, minus 3, you go till 3, 3. All the other possible combinations in between included, and each will correspond to one value of m. And this gives us the 16 possible values which dim and dqm can take. And with these values plugged in, you will get the exact signal SMT for a given value of m. That is what the Quam signal looks like. That's how the Quam signal looks like. And you have these 16 possible combinations. Now, what we can do is we can straight away go to the signal space. We can straight away go to the signal space. And before I go to the signal space, let me just say that the fact that the QAM signal has both its amplitude as well as the phase being modulated can be obvious from the way the signal looks. If you do a small manipulation to that signal SMT which I wrote earlier, it becomes clear, or it becomes more apparent as to how the amplitude as well as phase is getting modulated by the symbol. So SMT is root E naught. SMT is root E naught. DIQ, sorry, DIM root of 2 by Ts cos 2 pi f c t minus root E naught DIDQ m root 2 by Ts sine 2 pi f c t. Now, I am sure you know this representation. If we can say call this as, say, r cos theta, and this as r sin theta, we will have r cos theta into cos 2 pi f c t minus r sin theta into sin 2 pi f c t, which we can write as equal to r cos 2 pi f c t plus theta, isn't it? Because r, if you expand this using cos a plus p, you will get the same as this, provided you recognize this as equal to r cos theta and this excluding the negative sign as r sin theta. And of course r will be equal to, so since r cos theta this and r, so if you square these and add, you will get r square, because sin square plus cos square is 1, you will get r square. Under root r square is r, and hence r will be root 2 E naught by Ts dim square plus dqm square under root. And theta will be, if you divide this by this, you will get tan theta, and that will be dqm by dim. These will cancel off, and tan theta being dqm by dim, theta will be tan inverse or arctan dqm by dim. That means the signal SMT, that is our QAM signal, can be expressed as root 2 E naught by Ts root di square m plus dq square m cos 2 pi fct minus, or rather plus, tan inverse dqm by dim, because this is theta and this is r. And here you can see that diq and dim and dqm are responsible in determining the amplitude of the carrier wave. And of course, E naught is an energy, so in association with E naught, the energy of the signal is determined, that we'll see later. But essentially you can see that root E naught and root of d square im plus d square qm is responsible for determining the amplitude of the signal, and tan inverse dqm by dim decides the phase of the signal. So you can see that these symbols are together deciding the QAM signal's amplitude as well as its phase, and hence we say that QAM modulates both the amplitude as well as the phase of the carrier signal. So that's clear from this. Now let's move on to the constellation, the signal space. So again, with the help of this, we note that the carrier components or the basis functions are this. So it's again a two-dimensional signal space. It's a two-dimensional signal space. In phase quadrature axis, or phi 1, phi 2. Phi 1 is what we have here. Phi 1 is the in phase carrier component, and phi 2 is the quadrature carrier component, and these will be the coordinates, so to say. These will be the coordinates. So that includes the negative sign. So let's plot the constellation. Let's locate the signal points one by one, and from the table which we had earlier, so we'll use that table which we had earlier. So for m0, we have di0 as minus 3, dq0 as minus 3, and hence this will be minus 3 root E naught, and this will be, that is, this part will be 3 root E naught. That will be 3 root E naught. Right. So before I plot, I have to just have some idea here as to where I should locate the signal points. So let's say this is minus root E naught minus, I'm sorry, root E naught, 2 root E naught, 3 root E naught. Similarly, this will be minus root E naught minus 2 root E naught minus 3 root E naught, and minus root E naught minus 2 root E naught minus 3 root E naught, and over here we will have root E naught and 3 root E naught. So when m is equal to 0, di0 is minus 3 and dq0 is minus 3. di0 being minus 3, this becomes minus 3 root E naught. So in phase coordinate is minus 3 root E naught, and the quadrature dq 0 is minus 3, so minus 3 over here we will get 3 root E naught, 3 root E naught, and with that 3 root E naught we will have, remember the negative sign is included in the negative sign is included in the coordinate, so to say. So we'll get 3 root E naught. So we have minus 3 root E naught in phase and 3 root E naught as the quadrature. That means we will get this as the S0 or m is equal to 0. And then we see what happens for m1. When m is equal to 1, we get dim as, that is di1 as minus 3 and dq1 as minus 1. And you can now locate the in phase is the same as minus 3 root E naught. Quadrature becomes root E naught. So minus 3 root E naught and root E naught, that comes here, isn't it? Minus 3 root E naught in phase and quadrature is root E naught. Maybe we can see one or two more so that later you can. So m2, again for m2 di2 is minus 3 and the other one is dq2 is plus 1. So we will get minus 3 root E naught and minus root E naught. So somewhere here. This is for S2 and S3 will be here. You can verify, so we will not repeat the steps. And maybe S4, that is for M4, we have minus 1, minus 3 respectively. That gives minus root E naught and 3 root E naught. So that comes here. S0, 1, 2, 3, 4. And S5 will be here. You can verify this. If something is wrong, you can get back. S6 will be here. S7 and S8, maybe we can take a quick look. 1 minus 3, so root E naught and minus 3, there's this over here, and that will be S8, S9, S10, S11, And finally, the last column, so to say, S12, S13, S14, S15. So this is the signal constellation. You can see 4 points here, 4 here, 4 here, 4 here, that gives 16. And the partitioning of the signal space into decision regions is quite obvious. We can partition the signal space like this. So this is one partition, that is this part and this part, and the q axis included. That's a part of the partitioning, so I will not overwrite on that. And you can have similar partitioning like this horizontally as well. So this region, this is the way we partition. This region belongs to the signal S9T, or the symbol mapped onto S9T. So this region is belonging to that. This region for S10T, and this region for S13T, because all the points here are nearer to S13 than the other signal points. And this region corresponds to S12T. Similarly, this region corresponds to S15T. This region corresponds to S3T, for the reason that all points here are closer to S3T than the other signal points. So this is how we can partition the signal space into decision regions for each signal. So whenever you have received a QAM signal, you get R1, R2, and see in which of these decision regions you are landing with R1 and R2, or in which of these decision regions that point defined by R1, R2 lies, and then take a decision that the transmitted signal is the one which belongs to that region. Now, probability of error calculation is slightly complicated, as you can see from this, because when you think in general in terms of Mraquam, that can be quite difficult, in the sense quite involved, so we will not attempt that, but I would request you to take a look at this, how to calculate the probability of error of Mraquam, because I may give you an assignment on that later. Okay, now before we move on, there is one quick point to be made. So let's say we had the constellation like this. I don't want to show this in that same constellation because I have marked so many things on that. We had the constellation like this, and this was root E naught, 3 root E naught in phase and quadrature. Similarly, minus, I will not mark that, minus root E naught, minus 3 root E naught. Again here root E naught, 3 root E naught, minus root E naught, minus 3 root E naught. Now the signal points were 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now let's say that at a particular signaling interval, signaling instant, the signal transmitted was, let's say, this. This was signal transmitted, let's say. That is S12T is transmitted. Let's say S12T was transmitted. Now, S12T is equal to, now we know this is 3 root E naught. This is also 3 root E naught. So this is 3 root E naught, this is 3 root E naught. So this will be, using that 1 is to 1 is to root 2, we can write this as 3 root 2 E naught. This is 3 root 2 E naught. Remember, this is 3 root E naught, this is also 3 root E naught. So using the Pythagoras theorem, or the 1 is to 1 is to root 2 rule, which is the same as Pythagoras theorem, in a way it is applied Pythagoras theorem, you get 9 E naught plus 9 E naught under root. 9 E naught plus 9 E naught under root, and that will result in what we have here. So 9 square root of 9 is 3, and 9 root E naught plus 9 root E naught, you will get 18 18 E naught, sorry, 9 E naught plus 9 E naught gives you 18 E naught, and square root of that gives you root of 18 root E naught. Root 18 is 3 root 2. Right. So, and this angle is pi by 4. So S12T can be written straight away from this. It's just to show that the signal's amplitude as well as phase is getting modulated. S12T will now have an amplitude 3 root 2 E naught root 2 by Ts cos 2 pi FCT plus pi by 4. And similarly, you can see if it was S9T for that matter, this would have been root E naught, and this would have been root of 2 E naught, and the signal S90 would have been root of 2 E naught, root 2 by Ts cos 2 pi FCT plus pi by 4. Any other signal point, you can see accordingly the angle, the phase as well as the amplitude changes. So this signal will have an amplitude like this, S5T will have an amplitude like this, and its phase will be what we have here. So that is 90 plus 45. So that's the point. And of course, one before I move on, we can also have 64 QAM and 256 QAM. So in 64 QAM, you will have the di and dq taking values. So in 64 QAM, you will have them taking values -7, -5, -3. You can verify this later. -3, -1, 1, 3, 5, 7. And 256 QAM, you will have values from -15, -13, -11 till 11, 13, 15. And 64 QAM and 256 QAM are used in cable modem and digital cable TV. So with that, we will just continue further, and we'll try to identify what is the symbol energy, average symbol energy, because as you see, each signal has a different amplitude. So the signal energy is not the same for all the signals. So we will see that now. What is the average symbol energy? To calculate the average energy of a QAM symbol, because the QAM symbol amplitude, the QAM signal amplitude rather, varies from symbol to symbol, as we saw earlier. So to calculate the average energy, we have to approach the problem this way. Let's say we already have identified and defined the QAM signal. QAM signal is root E naught dim root 2 by Ts cos 2 pi of Ct minus root E naught dqm root 2 by Ts sin 2 pi of Ct, and this is in the interval 0 to Ts. That means the symbol interval is Ts. Now for the immediate next step, it's more convenient to express it like this, because we know phi 1 t is this, minus root E naught dqm, and we will express this as phi 2t. It becomes a bit easier to explain. Okay, so this is our Quam signal, and m can take on values, as you know, 0 to capital M minus 1. Now the energy of a particular Quam signal, say for a particular value of m, is calculated like this. It's a real signal, so s square mt dt, integrate from 0 to Ts duration, and this will be equal to 0 to Ts. This is smt, so root E naught dim phi 1t minus root E naught dqm phi 2t square dt. And when you square this, we can see what happens to this result. You square this, this is the square of this plus the square of this minus 2 into this term into this term. That's what you get when you expand this. Now square of this will be E naught dim square phi 1 square t integrate 0 to Ts dt will be 1, because phi 1 t is an orthonormal. It's one of the orthonormal signals. So its energy is 1. So E naught d1 di square m comes out of the integration. When you integrate from 0 to Ts, phi 1 square will get 1. So the result of square of this integrated from 0 to Ts will be E naught d square im. Similarly, the result of square of this integrated from 0 to Ts will be this, due to the same reason, because phi 2t also has unit energy. And then when you take the cross product, that is cross product in the sense minus of 2 into this term, when you integrate, you will effectively end up integrating phi 1t into phi 2t from the interval 0 to Ts, and phi 1t and phi 2t being orthonormal signals, the result will be 0. So this is the result of this integration. So the energy of a particular Quam signal, for a particular value of m, is this. Now dim and dqm take on different values depending on the value of m, small m. And now this is the energy of a particular symbol for a particular value of m. To calculate the average energy, we have to find the average of this, and for that maybe we can write average. AVG stands for average symbol energy is the expected value of this, expected value of E naught into d square im plus d square qm. And of course E naught is just a deterministic term, so that becomes E naught into expected value of this. So this, if you calculate, you will get the average symbol energy. And we note that dim as well as dqm take a set of values, that is, they take values from a range which we express like this. So isn't it? So this is what we had. So for example, if m is 16, that is if we are discussing 16 QAM, this would have been minus 4, so minus 3, and this would have been minus 4 plus 3 minus, so minus 3 minus 1, 1 and 3. 3 would have been this. That's what we saw earlier. So these are, so DIM and DQM take values from this independently. And this can be now expressed in a very compact form like this. For I taking values 0, 1, 2 up to root m minus 1. So you can now see that for I0 you will get minus root m plus 1, for I1 you will get minus root m plus 3, and for I root m minus 1 you can see that minus m plus 2 root m minus 2 plus 1, minus 2 plus 1 gives you minus 1, 2 root m gives you root m minus 1. So this way we can express the different values which DIM and DQM can take. So DIM as well as DQM take this value independently, and where I ranges from 0 to root m minus 1. So now we see that the number of possible values which DIM and DQM can take are m, because for each value of I, the I can take value from 0 to root m minus 1. That means I can take root m different values. It can take root m different values. There are root m values here. It can take root m different values, and hence DIM and DQM can take, you can see, root m different values. So again, if m is equal to 16, 4 different values, and these 4 different values which DIM and DQM can take are minus 1, minus 3, minus 1, 1 and 3. Okay, so now the expected value, that is the average of this, can be calculated. Let us first calculate the average of this, and then we can calculate the average of this. This expectation will be the sum of the expectations. So what is the average value of this? Now this is equal to, since this takes values, this is the value taken by this, we can write this as 1 minus root m plus 2i square. We can write it like this, because in general DIM takes on a value like this, where I ranges from this range. So again, I ranges from 0 to root m minus 1. Now that will be equal to, remember this I is an index which takes different values. Don't confuse it with square root of minus 1. So when I square this, I get 1 minus root m square plus 4 I square plus 4 1 minus root m into I, and the expected value of DIM square would be, now if we make the very reasonable assumption that the different values which DIM can take are all equiprobable. So as I said, DIM can take, and as well as DQM can take root m different values, and if they are all equiprobable, the expected value of d square im can be written as 1 by root m, that is the total number of values which this can take, and in the numerator you will have the sum of the squares of the values which d square im can take, and that will be nothing but the summation of this I equal to 0 to root m minus 1 1 minus root m square plus 4i square plus 4 1 minus root m I. So this summation applies to this entire term, that will be 1 by root m. This summation will simply give us 1 minus root m square, and you are simply adding 1. So when you remove this, take this out of the summation, you have a 1 here. You are simply adding 1 root m times, so you will get root m plus 4 into summation I0 to root m minus 1 I square plus 4 1 minus root m. If you want, you can change this to minus of 4 root m minus 1 into summation I0 to root m minus 1 I. So this will be the expected value of d square im, and since dim as well as dqm take the same set of values, the expected value of d square qm will also be the same. Now what we do is we use certain standard results which can also be arrived at quite easily. I use those standard results. The first standard result is that we know that summation n0 to n small n square is equal to 2n cube plus 3n square plus n divided by 6, and we also know that n, these are standard results. Of course, as I said, it can be derived, especially this one can be easily derived. This will take some time. Is equal to n into n plus 1 by 2. Now using this, we can write this. You can see there is a summation I square, I0 to root m minus 1. So you can use this over here, and there is a summation I0 to root m minus 1, and you can use this result over here. And then if you manipulate, which is a bit lengthy, simple but somewhat lengthy manipulation, you will have lots of root m's and m's which you will have to handle. So if you do that, I will not waste time here. It's simple, but as I said, somewhat lengthy. So if you do that, so the point is, this has to be, you have to use this result here, use this result here, and simplify this. You will get the expected value of this as equal to, the expected value will be m minus 1 by 3. And similarly, as I said, expected value of this will also be m minus 1 by 3, which means that the average symbol energy, which we found out to be E naught d square im plus d square qm, expected value of, will be equal to m minus 1 by 3, m minus 1 by 3. That's the expected value of these two, because expectation can operate on these two independently. So you will get 2m minus 1 by 3 into E naught. This is the average symbol energy of a Mraquam signal. So if m is equal to 16, you can see that it will be 10 E naught. So m is equal to 16, you will have 16 minus 1, 5 by 3, that is 5. 10 E naught is the average symbol energy. Average symbol energy for a Mraquam signal with m equal to 16. Now another interesting point before we wind this discussion is that if you take an Mraquam, if you take an Mraquam signal with m as equal to 4, what we will end up getting is nothing but QPSK. So we will end up getting QPSK if you take Mraquam with m equal to 4. So when m is equal to 4, the set of values which the two symbols take will range from, so m is equal to 4, so this will be root 2, I'm sorry, root 4, which is 2, so minus 1, and this will be minus 4 plus 3, which is 1. That is the end, because over here you will get 2 minus 1, which is 1. So di as well as dq take on values 1 and minus 1, and that gives us, when you substitute that into the general Mraquam signal representation, root E naught, dim can take on values plus or minus 1, root of 2 by ts cos 2 pi f ct minus root E naught. dqm can also take a set of values from this set 1 and minus 1, so plus or minus 1 root 2 by ts sine 2 pi f ct. This is nothing but the QPSK signal. You can go back and take a look. This is nothing but the QPSK signal. So Mraquam with M4 gives us QPSK, and that can also be, and we can also see what is the average symbol energy when for Mraquam. So Mraquam, the average symbol energy was derived just now, and it was seen to be this. So m is equal to 4. If m is equal to 4, you will get the result. If m is equal to 4, this becomes 6 E naught by 3, which is 2 E naught. And this is also something that we saw earlier when we calculated the symbol energy of QPSK. So that ends the discussion on quadrature amplitude modulation, and we'll continue our discussions in the next video.